Welcome back, Physical Science 20. So this is the 1.2 single displacement or replacement reactions section. So we'll look at observing and analyzing single replacement reactions, represent single replacement reactions using manipulative skeleton equations, bounce equations, etc., and learn how to name it. Determine the feasibility of a single replacement reaction based on the activity series, which we'll find out. Describe how the outcomes of various single replacement reactions may benefit or harm living organisms and affect the environment. So if you look over here, some people suffer from something referred to as nickel contact dermatitis, which is a skin allergy. The source of the nickel is the shiny metal parts of the cell phone that are in frequent contact with the skin. And of course, we're talking about these older cell phones, the old flip phones, the old T9s. So we have the buttons in their outer rim. The metal contains nickel. Nickel ions gradually leave the cell phone and transfer to the skin. Over time, constant exposure to nickel may make the skin sensitive to it. When sensitized, the next exposure can cause an allergic reaction. All skin naturally produces secretions such as sweat that is considered to be acidic. And of course, acidic means that the compound starts with H and is some negative ion with it, such as lactic acid or amino acids. These compounds make sweat mildly acidic. The acidity of skin is sufficient to slowly corrode the nickel from the cell phone. So if you look at the reaction here with lactic acid and nickel, key thing to note is this nickel and this hydrogen, which gives the lactic acid its acidic characteristic. So what we have happening here is this. The nickel is replacing the H in lactic acid. So it does. Nickel combines with C3H5O3 to become nickel lactate. And of course, hydrogen gets kicked out by itself. And yes, it's a Hofbrinkel element, so it becomes hydrogen gas. So with that, we can think of those two elements changing places. So the reaction of nickel with an acid follows the same pattern as other similar reactions. These reactions are called single displacement or single replacement reactions. So in a single displacement reaction, one element displaces or replaces another element. So here we go. We have A and B changing places. So you can think of it like this, actually. So let's say we have guy, girl. I'll make this guy orange. So we look at, can this happen? Is this guy, does he have what it takes to change places here? If he does, now he is in the relationship, we could think. And the orange guy is kicked to the curb here. So we can look at metals replacing metals in this case. So single displacement reactions are useful when you need to recover dissolved metal from solution. So for example, copper 2 sulfate is commonly used in labs. If a piece of reactive metal such as zinc is added to it, we can once again collect the lost copper. So take a look here. So again, the question is, so we have a metal and another metal. And then we have a non-metal group. So we're going to see, will this metal replace copper in copper sulfate? So that's a big question mark. In this particular case, it will. And we'll look at some rules that govern that. So zinc metal also reacts with solutions of many other metal compounds. In other words, we say that zinc is very reactive. It can replace many types of ions in compounds. Gold, on the other hand, rarely reacts, so it's not very active. This property explains why gold is one of the few metals that are found in nature, because it simply can't replace a lot like zinc. Most other metals exist only as compounds. Chemists use the word activity to describe how reactive a metal is. The more reactive it is, the greater the activity is. So the more that it can replace other metals in the compound. So we say zinc is more reactive than gold. The activity series of metals, chemists have experimentally developed an activity series a ranking of the reactivity of metals relative to each other. And we'll see it on the next page. The most reactive metals, lithium and potassium, are at the top, and the least ones are at the bottom. Hydrogen is included as well, even though it's technically not a metal. Since it forms positively charged ions, like a metal, it's considered to act like a metal. So the activity series is based on two important generalizations. So we should likely highlight these. One element can displace elements below it. So if you have your single element, it can displace elements that are below it from compounds in solution, but it cannot move above. And of course, the farther apart the two elements are, the more likely that the reaction will happen quickly. So it'll be the larger the difference, a strong and a more active one versus a least active one, it'll happen quick. So as we mentioned, the most reactive ones are lithium and potassium. Very weak ones are gold and silver, mercury, copper, and there's where hydrogen falls. And then the rest of them are somewhere around everywhere else. So to determine whether or not a reaction between an element and a compound will proceed, just look at the relative positions of the two metals in the activity series. And the key thing you're looking for, if the higher metal is the element, so that's the one by itself, then the reaction will happen. If the higher metal is the one that's in the compound, then nothing will happen. So if we look at an example, we'll see how this works. So using the activity series, write a balanced chemical equation for the reaction that occurs when we have magnesium metal, so that's the one that's by itself, and it's being thrown in a solution of copper 2 sulfate. If it's no reaction, just simply say no reaction. So we have solid magnesium, so that's the individual one, and copper 2 sulfate. And of course, copper 2, Cu2+. And if you look at our periodic table, we'll see that sulfate is SO4 2 negative, so they come together 1 to 1. So the key thing that we're going to look for here, does this happen? Will magnesium be active enough to replace copper? So let's make a note here. Mg must be, quote unquote, above copper on the activity series in order to replace it. So that's what we need to see, is magnesium above copper. So if I look here, here's copper, and magnesium, ooh, it's way up there. Way up there. So it will happen. So magnesium we think is, oh, it's more active than copper. So it has what it takes to change places here. So copper will be kicked to the curb by itself, but it'll be a solid. It'll come out as an actual copper solid. And then magnesium sulfate will be left over in solution, aqueous. And of course, magnesium is Mg2+. So like copper sulfate, it's 1 to 1. So this is balanced and everything. We could also predict, let's see here, 1, 2, 3, 4, 5, 6, 7, 8. So since Mg is 8 spots above copper on the table, or a chart, whatever you want to call it, this will be a very fast reaction. Okay, so the larger the difference there, the quicker the reaction will be. All right, let's look at this one. Using the activity series, write a balanced chemical equation that occurs when lead is placed in zinc nitrate. Okay, so lead, Pb, just lead by itself. It's not a Hofbrinkel, it says Pb, so we just write Pb with a little S designator, meaning solid. And zinc, if we look on the periodic table, we'll see it's 2+. Nitrate is 1 negative, so yes, we'll have to have 2 of those nitrates. So zinc, nitrate, but we have to have 2 nitrates, so of course that's where we use the brackets. Okay, so we're looking. Does lead have what it takes to replace zinc? So again, we have to see, is lead higher than zinc on the series? Let's see here. So here's lead, and oh, unfortunately, zinc is above here. So lead is not active enough to replace zinc. So PB is below Zn on the activity chart. Therefore, it is not active enough to replace it. So we just simply say, no reaction, sad face. All right, we'll leave it there, and we'll come back to this in part 2 and do some more examples.